Hello everyone, welcome to today's live broadcast entitled How to Select a Laser for Raman Spectroscopy. I'm Jerry Workman, the Senior Technical Editor of Spectroscopy, and I'll be your moderator for today's event. We are pleased to bring you this webcast presented by Spectroscopy and sponsored by Cobolt AB, a part of HÜBNER Photonics. HÜBNER Photonics manufactures high-performance lasers for analytical instrumentation as well as peer research. The Cobolt product line of diode-pumped and narrow-line lasers is perfectly suited for Raman spectroscopy as well as fluorescent microscopy. The Cwave product line of CW visible tunable lasers is the preferred source for any research lab doing tip-enhanced Raman research as well as nanophotonics research. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark Help widget in the dock at the bottom of your presentation window. I would now like to introduce today's speaker. We are pleased to be joined today by Dr. Håkan Karlsson, CEO and founder of Cobolt AB, a part of HÜBNER Photonics. Dr. Håkan Karlsson founded the high-performance laser manufacturer Cobolt AB in 2000. With a strong reputation for excellent quality CW lasers serving the life science and analytical instrument markets, Cobolt was acquired by HÜBNER to form HÜBNER Photonics in 2016. Thank you all for joining us today. Håkan, please get us started.
Hi, I'm Håkan. Thank you very much for the introduction. Welcome to this seminar. Thank you all of you who are joining today, and thanks also to those of you who are watching this afterwards. So we're going to talk about some of the aspects that should be considered when trying to select a laser source for Raman spectroscopy. And we're going to talk about some of the available laser technologies and how they differ between each other in performance parameters that are critical for Raman spectroscopy. And finally, with the help of my colleague Teresa, we're also going to show you a bit of how we here at HÜBNER Photonics are characterizing the performance of the lasers that we make, and in particular in regards to performance parameters important for Raman spectroscopy. I should say here from the beginning that we are limiting the scope of this presentation to be about spontaneous Raman spectroscopy. So we're mainly going to talk about single CW lasers. If you are interested in stimulated Raman spectroscopy or coherent anti-Stokes Raman spectroscopy using ultrafast lasers, I should warn you that you're probably not going to find much of interest in this presentation. So I will start by providing you with some background information on Raman spectroscopy, which you're probably already familiar with. So Raman spectroscopy is a powerful tool for material analysis and characterization because it's offering fast and sensitive and maybe most of all label-free chemical analysis. So it's largely non-invasive and typically doesn't require any sample preparation, which is very useful. So it's based on inelastic scattering of photons from a narrow linewidth laser source. The scattered photons are detected by a spectrometer and recorded in a spectrogram like this. And by studying the peaks, you get the chemical information on the sample. It requires a narrow spectral linewidth laser with high spectral purity for high resolution and sensitivity. So thanks to this characteristics of Raman spectroscopy, it has become a popular analytical tool across a wide range of different application fields. And thanks to a lot of development over the last couple of decades in laser technology and in filters and in detectors, Raman spectroscopy has really made its way out of the scientific laboratories. And it's not just used for material science, but also as a routine tool for inline process control and quality control processes in a wide range of different industries. So, for instance, in pharmaceutical development and production, Raman spectroscopy is routinely used for quality control of the raw materials, of the blend, and also of the compound distribution in finished pills. Raman spectroscopy is also starting to become an alternative to gas chromatographers for process control in petrochemical industries. It's being used in food and beverage production. It's being used in geoscience and archaeology. It's also used for gemstone control, forensics, and fraud protection in the field. It's also more and more commonly used in biomedical research, and it's also paving its way into clinical diagnosis applications thanks to its capability for rapid detection of infectious microorganisms and also with the potential of providing early cancer detection. So what are the basic requirements on the laser for Raman spectroscopy? So here we have a schematic picture of spontaneous Raman spectroscopy setup. We have a narrow line width laser source which is illuminating a sample. Most of the light is going to be Rayleigh scattered, but a small fraction of the light is going to interact with the molecules of the sample, excite some phonons, lose some energy, and get slightly frequency shifted. And by blocking the Rayleigh light or a Rayleigh scattered light with a filter and analyzing the frequency shifted light in the spectrometer and looking at these peaks that are coming out, it's possible to determine the chemical composition of the sample. And over here we have the main spectral properties of the laser, which is of importance for the Raman spectroscopy. So first we have the line width. How broad spectrally is the laser. So the line width has to be narrow enough so that the different neighboring Raman peaks can be resolved. However, it's not just the laser line width that limits the resolution of the Raman spectrometer. It's also determined by the spectral resolution of the spectrometer itself. And for a fixed grating configuration of the spectrometer with the detector array, the spectral resolution is determined by the groove density of the grating and the focal length to the detector array. And many advanced Raman spectrometers today, they can offer a spectral resolution down to a wave number or even a fraction of a wave number. Which means that in order for the laser not to be limiting the spectral resolution, the line width should be preferably way less than a wave number, which corresponds to a few tens of picometers in the visible range. Then they have the spectral purity of the laser, or the side mode suppression ratio, and that is how deep down you have to go from the main peak until you see some side emission from the laser source, and also how close this side emission is to the main peak. Because the Raman scattering efficiency is very low, so in order to be able to read out these Raman peaks, there must be no emission whatsoever from the laser source itself down to typically even more than 60 dB from the laser peak. Most of the material characteristic Raman peaks are located in this so-called fingerprint region, a few hundred to a few thousand wave numbers away from the laser. Those peaks can fairly easily be recorded by blocking the Rayleigh light or Rayleigh scattered light with the dichroic filter, which can offer up to 60 dB blocking at plus minus a few nanometers. However, in some cases it's of interest to study much lower Raman shifts, much closer to the main peak. And in order to study these shifts in the so-called low-frequency region, you have to block the Rayleigh scattered light with a more narrow notch filter, which can be done by using, for instance, a volume Bragg rating filter, which can offer 60 dB blocking at as narrow as plus minus 5 wave numbers. So, in terms of spectral purity for the laser, it has to be more than 60 dB, and for low-frequency Raman applications, it has to be that as close as a few wave numbers away from the main peak. For other more standard Raman spectroscopy applications, it's enough if it's a few hundred wave numbers away, or a few hundred picometers. Then there is the wavelength stability, because it doesn't help if the line width of the laser is very narrow, if the wavelength is drifting around during the acquisition time of the Raman spectra. So in order for the wavelength stability not to be limiting the spectral resolution of the Raman spectrometer, it has to be better than a few picometers over several minutes or up to hours, which it can take to record the Raman spectra. Then finally we have the wavelength. Where should the laser emit? And that depends on many parameters. So the choice of wavelength for Raman spectroscopy depends mostly on the material that is being studied. But there are also other aspects to take into account. First of all, we have the trade-off between the Raman signal strength and disturbing autofluorescence. So as I mentioned, the Raman scattering efficiency is quite weak, and it also scales exponentially with the wavelength with a factor of -4, which means that the Raman signal is much stronger at shorter wavelengths than at longer wavelengths. However, at shorter wavelengths you have much more influence of fluorescence background, which can easily drain the weak Raman peaks. Then you have also to take into account the detector sensitivity. The commonly used silicon-based CCD arrays in many fixed grating Raman spectrometers, the sensitivity of those are quite rapidly rolling off after 800 nanometers or over 800 nanometers. At longer wavelengths, it's possible to use detectors based on germanium or indium gallium arsenide, which also exists as arrays, but they are typically associated with a bit higher noise, which reduces the signal-to-noise ratio. And then, of course, another important aspect to take into consideration is that there has to be good availability of suitable laser sources at the wavelength, which is most optimum. An example of how the choice of the wavelength can influence the Raman sensitivity is shown here. It's several Raman spectra of polyimide taken by Yasuko Corporation in Japan. And we can see that the spectra, both at 542 and 785, the Raman peaks are drained by the background fluorescence, but the Raman peaks can easily be resolved when illuminating at 405. There's another possibility to avoid the problem of autofluorescence background, and that is to go further down, deeper in the UV for the illumination. Here you typically have even more fluorescence. However, typically the autofluorescence does not really appear until over 300 nanometers, which means that going deeper down in the UV opens up the possibility to both illuminate and record the Raman signals in this window here before autofluorescence sets in. However, challenges with UV illumination for Raman is that the high energy UV photons risks to damage the sample, and you have to use specific UV optics and go to different types of detectors. And then the availability of compact and cost-efficient sources suitable for Raman in this wavelength range is at least not yet so good. So with these aspects taken into account, it turns out that 785 nanometers is often offering the best balance between scattering efficiency, influence of fluorescence, detector efficiency, and here there is also a good availability of cost-efficient, compact and high-quality laser sources. 532 nanometers or other visible wavelengths are becoming more and more popular for inorganic materials such as carbon metals and so on, and also for resonance experiments. Down in the violet UV, those sources are suitable for biomolecules such as proteins and DNAs. And then for the most fluorescent materials, or the highly fluorescent materials, it's usually necessary to go to longer wavelengths, such as 1064. So these are some of the aspects that impact the choice of the wavelength for Raman spectroscopy. But there is more. For instance, there is a range of different instrumentation technologies for Raman spectroscopy that are addressing different application fields. We tend to sort these instrumentation technologies into these three groups, and they have slightly different requirements on the laser source. So we have probe-based Raman instruments that are providing quantitative data suitable for inline process and quality control. And here the lasers are coupled into typically multimode fibers into a probe, which is immersed into or put in contact with the sample that is being studied. Then we have very compact and small handheld Raman instruments like this one here, which are being used for in-field chemical detection and identification, for instance for fraud detection or drug identification. Here this eye safety aspects of the laser source can be quite important, and also the energy efficiency is important, as these devices are typically battery driven. Then finally we have microscopes, Raman microscopes, which can offer high resolution chemical imaging. And here the beam quality of the laser can be very important, or is typically very important. So in order to provide very high spatial resolution, the laser beams should preferably be diffraction limited, which means that they should be single transversal mode, or so-called TM00 mode. And if that was not enough, there is a wide range of sub-variations of Raman spectroscopy that also puts slightly different requirements on the laser source. And most of these are sub-variations to microscopy, but not all of them. For instance, there is a possibility to enhance the Raman signal with several orders of magnitude by combining the sample with a metal surface, either by putting the sample on a metal coated surface, and then we're talking about surface enhanced Raman spectroscopy, or by aligning the illumination with the tip of an atomic force microscope, which is also normally coated with a metal. And then we're calling it tip enhanced Raman spectroscopy. Both these techniques are often using visible lasers, and they are able to provide very, very high spatial resolution down to single molecule detection and sub-diffraction limited spatial resolution, which is very powerful. Raman spectroscopy can also provide chemical detection across optical barriers. like for instance inside a container. And this is achieved by so-called spatially offset Raman spectroscopy. And here one is utilizing Raman scattering from scattered light that goes into the container through the optical barrier. And the Raman signal is detected by focusing the detection to a spot slightly aside from the illumination spot. And here it's common to use a bit longer wavelength, typically over 800 nanometers, in order to have better penetration through the container wall. It's also possible to enhance the Raman signal very much by overlapping or choosing a wavelength that is overlapping with an absorption band of the material under investigation, so-called resonance Raman spectroscopy. And this is even if also the fluorescence is usually then increasing very much. For resonance Raman spectroscopy, it can be very beneficial to work with a tunable laser source to be able to find the right resonance effects. It has also been shown that it's possible to suppress the impact of background fluorescence by recording two Raman spectra with two laser sources slightly shifted in wavelength. And by subtracting those spectra, the broadband fluorescence background will be eliminated, but the Raman peaks will remain. This sounds very promising, but it requires illumination with two lasers that are spectrally shifted with just about half nanometer or 1 nanometer quite shortly after each other, which can be a bit challenging. As I mentioned earlier, there is in some cases of great interest also to look at smaller Raman shifts or Raman shifts in the low frequency region, which is also called terahertz Raman in the terahertz region. Terahertz Raman gives access to molecular lattice vibrations in the sample. And this can be very interesting for determining the crystallinity of pharmaceutical substances, which in turn is very important to control the therapeutical efficiency of a drug. But in order to record Raman spectra in the terahertz region, you have to work with a laser source which has very high side mode suppression ratio or spectral purity, very close to the main peak, so as close as a few wave numbers from the main peak, which is a few hundred picometers in wavelength. There's also standoff Raman. In this case, it's possible to measure or do chemical detection at several tens of meters away from the spectrometer. And this can be used, for instance, for explosives detection. But in order for this to work, it's necessary to work with high energy pulse lasers, such as nanosecond Q-switch lasers with very high peak powers. And finally, if you're working with very fluorescent materials, it's common to work with Fourier transform Raman spectroscopy. And here the Raman signal is read out from a Michelson interferometer, where the arm length is varied over time. And the Raman signal is detected with a single element detector. And in this way, the fluorescence background can be suppressed. And for this kind of Raman spectroscopy, it's common to work at longer wavelengths, such as 1064, to minimize the fluorescence. So what are the most common laser technologies for spontaneous Raman spectroscopy? The most common ones are diode pumped single frequency or single longitudinal mode lasers with various types of nonlinear optical frequency conversion, and frequency locked semiconductor lasers. And the frequency-locked semiconductor lasers can be divided up into two groups. Either the semiconductor is locked to a grating structure which is built in on the semiconductor chip itself, and we're talking about DBR or DFB lasers. Or the semiconductor can be locked to the narrowband optical feedback from an external grating element, such as a volume Bragg grating element, and then we call it external cavity lasers. The diode pumped single frequency or single longitudinal mode lasers, they're built up like this typically. There is a broadband semiconductor that is pumping a laser material or laser gain material. One builds a laser cavity around this, which emits somewhere in the near infrared typically, and then the output is converted into the visible by a nonlinear optical conversion element that is typically put inside the cavity to make use of the high intensity intracavity circulating field. And then we get output in the visible. And by using cascaded nonlinear optical elements, you can take this further down in the UV. And these lasers are made to operate on one single longitudinal mode, but by various types of intracavity frequency filters. So these types of lasers are having slightly different characteristics in some of the performance parameters. The diode pumped lasers, I should say, these laser materials are typically made of rare earth doped crystals such as neodymium YAG or neodymium vanadate, but they can also be of semiconductor types. The diode pumped lasers provide typically a very narrow line width emission of way less than a megahertz width, and very good spectral purity, very close to the main peak. Side emission from this kind of lasers are usually coming from parasitic lines, and they are typically several nanometers away from the main peak and can easily be blocked off by dichroic cleanup filters. These lasers are typically also offering very good single transversal mode beam quality or TM00 beam qualities, Gaussian beams or diffraction limited beams that can be focused down to very small spots. Here I should say that one has to be careful when talking about single mode lasers, because they can either be single longitudinal mode or single transversal mode. Most of the single longitudinal mode lasers are also single transversal mode, but not all single transversal mode lasers are single frequency or single longitudinal mode. So one has to be careful with the term single mode lasers. The frequency locked semiconductor lasers have a bit different spectral properties. They can be operating as a single frequency or narrow line width depending on the output power. But there is always a broadband side emission here down at around 40 to 50 dB from the main peak that is coming from amplified spontaneous emission from the diode laser. In order to be able to use this kind of lasers for Raman spectroscopy, you have to have a spectral cleanup filter. Either you can use a dichroic cleanup filter like the yellow here, which provides spectral purity of more than 60 dB, normally a few nanometers away from the main peak, which is typically okay for Raman spectroscopy in the fingerprint region. But if you want to use this kind of laser for a low frequency Raman, you have to filter it with a more narrow bandpass filter, such as a volume Bragg grating element. These kind of lasers, both DBRs and external cavity lasers, can offer TM00 beams, but they are typically not quite as nice as the diode pumped lasers. The DBR lasers are usually power limited to a few tens of milliwatts, but it's possible to scale the output power level with this kind of lasers by doing external cavity locking of multimode lasers. This can take the power up to several hundreds of milliwatts or even watt level output power. But then the beams are multimode, looking more like a square like this. But that's usually good enough for coupling this efficiently into multimode fibers. The frequency locked lasers can be provided in very compact packages, typically butterfly packages with compact pigtailing. They can also be provided as self-contained laser modules with completely integrated electronics and beam shaping. This is also the case for the dye pump lasers, which are also usually coming as self-contained modules with integrated electronics or with electronics as a separate unit. So in summary, some pros and cons with these types of laser technologies we can summarize. The dye pump lasers have excellent spectral purity and beam quality. They have very good wavelength stability and repeatability, so most of the lasers are coming out with the same wavelength. They are power scalable up to several hundreds of milliwatts or even more than several watts of power. They have become more and more readily available across the visible wavelength range, from the blue up to deep red, and also in the near infrared from 900 to 1300 nanometers. However, the cavity design is a little bit more complex for these lasers, which means that they have a bit lower efficiency and are a little bit more bulky. The frequency locked lasers can be, especially for the case of DBR and DFBs, they can be very cost and power efficient. They are readily available across the range of 700 to 1100 nanometers. And thanks to an increasing availability of external cavity lasers, they have increasing availability also in the visible and in the violet. However, they're a little bit less power scalable than the dye pump lasers, and they require spectral cleanup filters to be used for Raman spectroscopy. These kind of lasers is also more sensitive to optical feedback. Also the dye pump lasers can be sensitive to very well aligned optical feedback from the sample, which can be the case if they are being used in a confocal configuration. The impact on these lasers is usually that they have slightly increased intensity noise, but most other parameters are remaining the same. However, for the diode-based lasers, they can actually get permanently damaged by well-aligned optical feedback. So for this reason, we typically recommend to have an integrated optical isolator when working with this kind of laser for Raman spectroscopy, especially in microscopy configurations. All right, then we have the topic of ensuring stable spectral performance over time and varying ambient conditions. So it's one thing to be able to achieve a very good spectral performance from these lasers for Raman spectroscopy. It's another thing to be able to ensure that this performance remains over long time scales and over varying ambient conditions. Most of these lasers, except those that are built on a pure chip basis, they consist of multiple optical elements which need to be very well aligned towards each other in order to maintain the spectral performance of the laser. So in order to ensure very good reliability of the spectral performance, this kind of lasers need to be assembled using some kind of sophisticated technology for optics assembly. For instance, an example of that is the H-Secure technology, which we are using to produce the Cobolt product line. And the H-Secure technology is based on high temperature curing of miniaturized optics that are mounted onto temperature controlled cavity platforms into hermetically sealed packages. By producing lasers in this way, we can see that the lasers maintain their spectral properties even after hundreds of times of temperature cycling them between minus 30 to minus 70 degrees Celsius, and after mechanical shocks up to over 60 G, and also after continuous operation over several years, up to 5, 6, 7 or even 8 years. So speaking of Cobolt, I will tell you a little bit more about what lasers suitable for Raman spectroscopy are offered on the Cobolt product line. So on the Cobolt product line we have several different product platforms with performance suitable for Raman spectroscopy. We have the Cobolt 08, 04 and 05, and they're slightly different in their package dimensions and their electronics. The 08 lasers have self-contained electronics and compact format, and the 04 have separate controller electronics. We're working with different types of laser technologies in these product platforms. Most of these lasers are made as single longitudinal mode diode pump solid state lasers, either as standing wave cavities or as ring cavity lasers in the 0501 platform. We also work with volume Bragg rating locked diode lasers on the 08 NLD platform. With the diode pump solid state lasers, we are covering wavelengths from 355 in the UV over most wavelengths in the visible, from 450 in the blue over green, yellow, red, up to 1064 in the near infrared, with up to several hundred milliwatts of output power, or even more than a watt of output power in the 0501 series. And with the VBG locked diodes, we're covering the violet at 405, the 488, 633 and 785 nanometers, which are all very commonly used for Raman spectroscopy. And at 785 we have two versions, one single transversal mode laser at 120 milliwatts and a higher power multi-transversal mode laser. The line width of the diode pump lasers is specified to well over or well less than a megahertz, and typically for the VBG locked diodes to less than a picometer. We're also specifying the spectral purity of these lasers of more than 80 dB with or without integrated cleanup filter, and we also specify how close to the main peak we're achieving this spectral purity. In case of the diode pump lasers, we are achieving the 80 dB very close to the main peak, well less than 5 wave numbers required for low frequency Raman spectroscopy. In the case of the VBG locked diodes, we are achieving 80 dB at plus minus 5 nanometers. We also have a special version of the 785 nanometer laser with a self-integrated VBG filtering function, so that we can achieve over 60 dB as close as 300 picometers away from the main peak, which make that laser also suitable for low frequency Raman spectroscopy without any further external filtering. We specify the wavelength stability to less than a picometer over hours of operation and a couple of degrees of ambient temperature variation. Most of these lasers are having an output which is single transversal mode TM00, which can be efficiently coupled into single mode polarization maintaining fibers. The higher power 785 is a multi-transversal mode laser, which can then be coupled into a multimode fiber with about or down to 50 micron core sizes. We also offer optical isolators integrated as standard typically for the VBG locked diodes, and as an option for integration into the 08 and the 04 diode pump lasers. The 0501 lasers are ring cavity designed, which means that they are pretty much immune to optical feedback. So it's there's a lot of wavelengths that can be covered with compact lasers suitable for Raman spectroscopy today. It's a large selection. If it's still difficult to pick which is the best wavelength for a particular Raman experiment or for a particular Raman spectroscopy setup, an option is of course to combine several of these laser sources into a laser combiner. At HÜBNER Photonics, we offer a range of different laser combiner solutions on the C-Flex platform, which can combine from 4 of the different Cobolt lasers up to as much as 10 of the different Cobolt lasers, which can be picked from various product platforms across the 08, 04, and 05 series. And here the beams are aligned into one overlapping beam that can be efficiently coupled into single mode polarization maintaining fibers with 1 or 2 ports. And these laser combiners are easy to install in the field, and they're also possible to upgrade by the user itself in the field with more lasers. And they can also be offered with high speed intensity modulation capability. If it's still difficult to find the absolutely right wavelength, there is another option, and that is to work with a broadly tunable laser source, such as a Cwave, which is also produced by HÜBNER Photonics. This is a broadly tunable single frequency CW optical parametric oscillator with built-in frequency doubling. It exists in a couple of different configurations, which is capable of offering several hundred meters of tunability across the visible, from the blue to the red, or from the green to the deep red, and corresponding in the near infrared from 900 to 1300 nanometers and 1000 nanometers to 1500 nanometers, with more than 200 milliwatts of output power in the blue and more than a watt of output power in the near infrared. And this C-Wave source is offering single frequency emission across the whole wavelength range, excellent spectral purity of more than 60 dB, and very good wavelength stability. And it can also be locked to an external source. So this could be a very suitable choice for delicate resonant Raman spectroscopy applications. So with this, I will hand over to my colleague Teresa, who's in the lab, and who will show you a little bit of how we characterize the performance of the Cobolt lasers, and especially in terms of these performance parameters that are important for Raman spectroscopy. So the line width, the spectral purity, and the wavelength stability.
I'm Teresa, coming to you live from Cobolt. I'm the technical quality manager here, and we're going to be looking around our manufacturing and test facility to see how we verify some of our key performance parameters. I'll be showing you the tests that we do on our lasers for Raman for bandwidth, spectral purity, and wavelength stability. All of these parameters everything is contained right here in this small laser head. The laser, the optical isolator, and the control electronics. So once you plug it in, turn the key, you're ready to go. No adjustments required. Here we have a Cobolt 08 NLD at 405 nanometers. It's mounted on a temperature-controlled base plate and shines at different ambient conditions. In this measurement setup, we have an 08 DPL laser at 532 nanometers. The 08 DPL lasers are diode pump solid-state lasers, whereas the 08 NLD lasers are frequency-stabilized diodes. Here we have the spectral purity over the entire specified ambient temperature range. At this test station, we have another Cobolt 08 NLD, but this one is 785 nanometers. Here we have the light coupled into a fiber, which is coupled into a wavelength meter, and we can monitor you can see the wavelength stability performance in temperature cycling. So this 4 picometer range is the entire span over 20 to 50 degrees on the base plate. Here you see the temperature cycle as monitored by the control software. Thanks for joining us here in our
Here's a quick summary of what we are talking about. We have concluded that Raman spectroscopy is a very useful tool for chemical analysis and detection across a wide field of scientific and industrial applications. There are many different variants of Raman spectroscopy that set different requirements on the laser source. The main laser requirements is narrow spectral line width, high spectral purity, a good wavelength stability, and picking the right wavelength. And for confocal imaging, it's important to have a good TM00 beam. It is also important to have a good manufacturing technology and detailed verification testing to ensure that the spectral properties remain over time in varying ambient conditions. And finally, there is an increasing availability of suitable lasers for Raman spectroscopy over an increasingly large range of wavelengths. And they're also possible to integrate multiple of these laser sources into laser combiner solutions with or without fiber coupling. And finally, there is also broadly tunable lasers suitable for Raman spectroscopy available. So thanks again for listening. We'll be happy to try to answer your questions if you have any.